Hello, and welcome to my talk with Elliot Saba about what is new in PKG, artifacts, binaries, the package protocol, and more. So before we begin with that, getting into the details, let's talk a little bit about the overall vision of PKG. So there's been a huge amount of work done on it, the package manager, since long before 1.0, and a lot since. What is the end game? What are we trying to get at? And the bottom line is that we want to enable users to get working code easily, quickly, and reliably. Or another way to put it, which Elliot came up with, was installing packages should just work. It should just work quickly, and it should just work every time. So key pieces of what we need to make that happen are reproducibility. We need to record what was done, what was used, what the exact code dependencies were. Immutability, so if you record something, it doesn't ever change. And infrastructure that is reliable to make sure you can get all of that again in the future if you need it. So some of what we're going to talk about has already been released in past Julia versions. So Julia 1.3 introduced artifacts. Julia 1.4 introduced the package protocol, although it was not on by default. Julia 1.5 flipped the switch so that the package protocol was used by default and connects to pkg.julialang.org. And that was a pretty small client-side change, but there was a lot of infrastructure work required to make it happen because we'd had to have a global network of package servers in order to serve packages efficiently to all of the Julia users in the world. Okay, so the problem we were trying to solve when we came up with artifacts was that building binary dependencies on clients is extremely unreliable. Anybody who's ever tried to use the earlier package manager that to install packages that had binary dependencies, or many other programming language package managers that try to build client-side code will have experienced this. Sometimes it works, especially if the dependency is really simple, but a lot of times it doesn't. So some of the problems that can happen are the client may not have a compiler at all. It may have a compiler that is of a wrong version that's incompatible with the dependency that needs to be built. It may depend on other binary dependencies that are not installed or of the wrong version. There's just a million things that can go wrong. So what we want instead is to just be able to download pre-built binary dependencies and just run them as is. Because then nothing can go wrong on the client. So it's a really incredibly reliable situation if you can make it work. In the process, we realized that this is not all that different from supporting shipping large data files to users, because shipping large data files inside of packages is wasteful and kind of not great. Large data doesn't really belong in version control. It should be source only. And if you ship it with every copy of a package, then that means there's no sharing, and every time you install a different version of the same package or a different package that depends on the same data, there's multiple copies. And so you can end up with lots and lots of copies, which is especially not good if the data is large. It's fine with source, but not great for large data sets. So our solution is that we introduced this file called artifacts.toml, which is in toml, which is the standard file format we use for all the package manager related files. And what this toml file does is it allows you to associate a name with a piece of content, which is a file tree that we hash cryptographically the same way Git does to get a hash that identifies exactly that source tree, and then we map that to a name. And the name is what you use in the code to refer to that content. And because it's content addressed, that anybody using the same content hash is referring to the exact same file tree, so it can be shared safely among different packages and different versions of the same package. And it's immutable. You do not change it ever. So it's safe to do that. Now, the features of the artifact system that make it good for binaries and libraries are that it supports system-dependent content. You can use the same name and associate it with a different tree depending on different features of your system, like the OS you're running, the hardware, the features, the ABI, all of these things that make it necessary to have different versions of binaries or libraries. So what this allows us to do is to get fast working binaries that are tailored to each system. And recently introduced, you can even do this tailored down to different variations of the same architecture. So, x86 with certain features turned on for performance. Of course, generating all of these system-dependent binaries and libraries is tricky. It's a lot of work. But there's this amazing system that has been created called BinaryBuilder, which automates generating these platform-specific artifacts. And Elliot is actually going to give a talk at another time slot that is all about BinaryBuilder. So I really encourage people to take a look at that. It's pretty mind-blowing stuff. So in previous versions, the package manager just downloaded things directly from GitHub, GitLab, wherever they're hosted, using a variety of protocols, HTTPS if that's what you were using, SSH sometimes, raw Git protocol, whatever the configuration was. So there's a bunch of problems with this. It was actually pretty effective, a great way to bootstrap a package ecosystem, but it's not without its problems. So one really big one is vanishing resources. So if someone deletes their package off of GitHub or makes it private, then no one can install it. It just goes away. And we don't have a way of caching it or anything. We can kind of recover from that situation if someone has a copy, but it's not automatic. And it can break things for a long time if someone does that. Famously, this happened in the NPM Node Package Manager ecosystem when someone rage quit and deleted the left pad package, and tons of production code broke in the JavaScript world. So another problem is that, downloading and installing stuff directly from these, Git host services is it really, really tightly couples the system with GitHub and the Git protocol. And there's nothing inherently making Julia package management tied to Git or GitHub. It would be nice to decouple these. Another issue is that, since you're downloading packages from a whole variety of different places over different protocols, it's a nightmare for firewalls and sysadmins. It would be much better and much simpler if we used one host and one protocol that could be, whitelisted in the firewall, and then everything will just work. So that's the goal. It would also be even nicer if it was really trivially easy to put up a caching server inside the firewall, so that if they don't want to punch a hole through their firewall, they can actually allow people inside of an organization to get Julia packages easily without having to do that. Another issue is that we have no visibility currently into what packages are popular because they're downloaded directly from GitHub, usually as tarballs, and we don't get download stats on that because GitHub doesn't offer them. They offer limited clone stats, but most people don't clone packages as Git repos. They just download the tarballs because it's much faster. But then we have no idea what people are installing. Performance is not ideal. It's great if you're in North America. It's pretty bad in other places. I have heard of package updates taking tens of minutes in Australia or China. And so we'd really like to address that so that everyone everywhere in the world has a great experience installing and updating their Julia packages. Okay, so our solution is a thing called the package protocol. It's a really simple HTTPS protocol for downloading registries, packages, and artifacts, which are the three types of things you need to do any sort of package operation, and that covers it all. It is content addressed, which means that you ask for the content that you're downloading. So you say, I want the registry with this UUID at this exact tree hash. And then that you get a tarball, a compressed tarball of that, and that is perfectly cacheable because of the content addressing. It means, that will always, a tarball for that tree will always be valid because the tree doesn't change. You're asking for that specific content. And this seems pretty simple, but it addresses all of the problems on the previous slide. The only downside is that it requires us to run our own servers. And we have done that, and Elliot has been a rock star there. He's the guy who runs the servers and has made this system possible. Now this was not on in by default in 1.4. You had to set the environment variable Julia PKG server. That was because we didn't, have the infrastructure set up initially, and we wanted to have time to build out the infrastructure before making it the default. So in 1.5, we did make it the default. So we flipped the switch, and now by default, the package client connects to pkg.julialang.org. Unless you set the environment variable Julia package server, you can set it to a different package server, or you can set it to the empty string to opt out of using the package protocol at all. So there's not many client-side changes in this release, actually. It was mostly getting server-side infrastructure ready, but that's been done, and it was a large amount of work, but really, expertly done by Elliot. The package server is open source. It has been from day one. You can find the source at this URL. And now we have a global network of package servers running all around the world, serving people packages. So here's our rough plan for world domination. You can see on this map that we have 10 package servers all around the world, 2 storage servers. The package server is a cache strictly. It's ephemeral. You can delete one, you can bring it up, you can bring it down. Doesn't matter if you completely delete one. The storage server has to remember everything it serves forever and is the persistence layer, but it serves a lot less traffic because it only serves 2 package servers which cache everything, and we have a phenomenal cache hit ratio. You can see here that these servers are all around the world. 1 and 3 are where the storage servers are, but there also is a package server at that location, so it's both. We'd really like to get more servers around the world. You can see that there's large parts of the globe that aren't currently, super close to a package server. That's because the Lightsail service that we use on AWS doesn't have regions there yet, but as soon as they have regions there, we will deploy more package servers. In particular, we get a lot of traffic in China, and you can see that there's three servers in the Chinese region. And in Australia, we have a package server that is local to the continent, and that means that people in Australia don't have to wait tens of minutes for package updates anymore, which is great. So this is the general. I'm going to talk about the flow of a package protocol request, like what happens here. So the package client, pkg.jl, which is built into your Julia client, makes a request for one of these things. Let's say it makes a request for a package at with a specific UUID and tree. So it makes that HTTPS request to the package server, and the package server, in the most common case, looks in its local cache and finds that tree already exists there. It has it locally. So the package server loads it and then serves it back to the client, and the client gets their tree and does what they need to do. That is all very fast because you should be talking to a package server that's close to you, and it's in local cache, so it's fast to serve. However, that is not always the case. Occasionally there's a cache miss, and the package server makes a request to the package client makes a request to the package server, and it doesn't have something in the cache. Oh no. So then it has to go talk to the package server. Now the package server has everything. So if the package storage server doesn't have it, then it doesn't exist from the perspective of this system. So the storage server gets it, returns it to the package server, which sticks it in the local cache, and then serves it back to the client. So this takes longer, but it's relatively rare. And then after this, the package server will have it in local cache and serve it quickly forever after. All right, so now I'm going to talk about future releases, specifically 1.6. So 1.6 is going to be a huge release from the perspective of the package manager. Features include resource diffs, which give us faster updates of everything. Artifacts rework, which means faster loading of binary dependencies and packages that have binary dependencies. So that's a huge improvement. Scratch spaces, which allow cached mutable state without having to mutate the package content itself, which is we don't want. And then preferences, which allow global configuration of packages, again, without mutating the state of the package itself. And I actually think that with these 4 features in 1.6, we're pretty good on the package manager for the foreseeable future. I don't have any, there's no big outstanding issues that I have after this. Of course, we'll do bug fixes and improvements, but I think that really will be a solid release to say this is a complete system now. Okay, so resource diffs. What's the issue that this feature is trying to address? Well, let's say you already have a version of something, a registry, a package, an artifact, and you want to update it. So let's say you had a registry update last week. You want to update it again. Do you really have to download an entire new copy of the registry? It's a pretty big, tarball. It's like one or two megs compressed, which is, not enormous, but it's big enough that maybe if you're on a slow connection, you don't want to download the whole thing. Well, of course, we have technology that can address this. Diffs are a thing. So what we would like to do is, instead of sending you the entire new copy of the registry, send you a diff from the previous time you downloaded it. Okay, so the solution here is send tarball diffs using bsdiff, which is a very standard binary diff tool. And the URL protocol schema is, you ask for the URL registry / UUID of the registry, and then the hash tree of the new version minus the hash tree of the old version, where the old version is the one you have and the new one is the one you want. A couple of details here. You don't want to do diffs of compressed data. That doesn't diff very well. So what you want to do is you want to take a diff of the uncompressed tarball and then compress the diff. So that's what we do. Another issue that, there's a few other issues that make this trickier than it seems naively. So portability is a problem. The bsdiff tool was built for BSD. The name kind of suggests that. It works great and compiles on Linux and Mac OS and other Unix systems. It does not compile on Windows, so it would need to be ported for that. But there's another issue which is actually a little trickier, which is that in order to make this whole system efficient, it turns out that most of the work to create a diff is actually creating an index of the old content, which is good because that means that if you've created that index once, you can save it and reuse it when you have to create a diff for the same old content to a different version of the new content, and that scales pretty well. However, the bad part is that the bsdiff tool has no API for implementing that. It just turned out to be very tricky and nasty to hack into the C code. So between the need for portability and being able to reuse the index, I ended up just implementing a pure Julia implementation of the same bsdiff tool, and added an API for computing an index and reusing it. So that worked out really well, but it was quite a bit of work. So another sort of tricky issue is that if you're going to apply a diff to the old tarball, you have to have the old tarball. So the problem there is that we download tarballs, but then we extract them and put they scatter a bunch of files on disk. We don't want to hang on to the tarball after we've done that, because that's doubling the storage requirement of the whole system. So then when we want to apply a diff, we need to reconstruct the exact old tarball or the diff won't apply. So how do we deal with that? And the solution we ended up coming to is that we record what we call a skeleton file from the tarball. So basically it's the part of the tarball that you don't extract into files. It's the headers for each of the files, and you just pack those together and compress them and save them as a skeleton file. And then you can combine the skeleton file with the unchanged files on disk to reconstruct the exact tarball that you had. If the files have changed, then that won't work, but they're not supposed to change because these things are supposed to be immutable. So now I'm going to hand things over to Elliot. He's going to talk about improvements to artifact handling in 1.6 and scratch spaces and preferences, which are all really, really exciting new features. Thanks for watching my part of the talk.
I'm really quick going to go over some of the new features that we're going to be putting into Julia 1.6 for the package ecosystem. The first, and dearest to my heart, is a rework of artifacts and JLL packages. Now, JLL packages are the API for wrapping binary dependencies that is expressed towards other packages in the Julia ecosystem. This includes executables, as you can see here, using something from Git to run Git status, libraries, creating a 0MQ context from the 0MQ JLL package, and of course just plain files, such as reading in the contents of a header file. The piece that JLL packages provide are these pieces highlighted in red: the function calling git to get the path to the git executable, the constant to pass into ccall to call a function inside of libzmq, and of course the path to a file on disk. Now, there's a problem with JLL packages, which is that they are somewhat slow to load. In particular, initialization is slow. Imagine if I have a baz.jl package, and it has a libbaz JLL that was generated through BinaryBuilder, and it uses something out of libbaz.so. If I have another package, foo.jl, which itself has a binary dependency, and that binary dependency also depends on libbaz.so, everything is fine and happy. However, if libfoo.jl has another binary dependency, and that binary dependency depends on something that baz.jl itself doesn't directly use, we could run into a problem where that libcux.so is not easily findable by libfoo. The way that we're dealing with this right now is by just eagerly opening all libraries every time you open a JLL package. This is a fundamental restriction in the flexibility that we have when using that kind of ccall syntax. And so, in order to try and speed up JLL packages, we're actually going to be taking the ccall syntax and improving it such that we can change a call from a constant to the result of a function, so that that function can lazily load all necessary libraries in order to absolutely minimize the amount of work that we have to do when loading JLL packages. There's also some other things that we're going to be changing in 1.6, such as splitting the artifacts module out of PKG so that there's less code for the compiler to deal with overall. But the combination of all these efforts should result in us having a significantly faster JLL package load time in 1.6. Another thing I'm really excited to share with you guys is scratch spaces. As Stefan has said time and time again, we want packages to be completely immutable. As the saying goes, an immutable package is a happy package. But sometimes you really just need to write out some files. And if you're not writing them into the package directory and not into temp, then where can you write them? Introducing scratch spaces, which will give you the key macro call getScratch, which provides a namespaced writable directory for your package. That directory will exist as long as your package does, and once your package is removed from the user's machine, either through an upgrade or because they're not using it anymore, it will get garbage collected along with the rest of the package and artifacts that were installed. This is not meant to replace artifacts. It's a completely separate idea. One is mutable, the other is immutable, one is distributable. This is not distributable, but it provides a space for packages to write out any kind of temporary files, any kind of build artifacts that are specific to that machine, etc. Another piece of functionality that we're excited about is preferences. Some packages need persistent configuration. You can imagine a package that has multiple backends that it can choose from, and it may be up to the user to decide which one is best on that particular machine. Some of these preferences need to happen at compile time rather than runtime, because the package needs to know which backend to use when it's generating code. Preferences are key value stores that will get stored within top-level project.toml files. These preferences can have defaults applied from the depot level to allow the machine to have an overall default of using the CUDA backend, for instance, but a user could override it to use the CPU backend if they need to do something special. It's an extremely simple API, essentially just a load, save, modify that stores dicts within your project.toml, and modifying preferences will cause recompilation upon the next load of your module. This is what allows users to change preferences and then have the packages reflect those changes in their pre-compilation caches. With that, we are open for questions. Thank you very much for attending our talk.